Hello, everyone, and thank you for being here. My name is Umair Shahid. Thank you for the introduction and everything. First up, apologies for knowing absolutely nothing about the Turkish language. I will have to speak in English, and please bear with me as I do that. In case during the course of this presentation, if something is not clear, if you feel I'm going too fast, if there's any question, feel free to interrupt. I'm happy to slow down and explain. So the topic of our conversation today is Postgres performance. It's oriented towards application developers. So first up, maybe a show of hands. How many DBAs in the audience? Okay. How many developers in the audience? All right, so kind of like an even split. How many people who have never heard of Postgres? Thank you. Okay, so who am I? If you do a select star from Umair, that's what you're going to see. I live in Islamabad, Pakistan. That's where I flew in from yesterday. And I've been working in the Postgres space for 20 years. I started off in 2003, well actually a little over 20 years. I'm the founder of Stormatics, which is a professional services company, and I live in Islamabad with my wife, 2 kids, and my mother. And well, actually, over the course of these 20 years, I have worked with different pure-play Postgres organizations like PGDay, OpenSCG, Second Quadrant, and Percona. And now I run a professional services company by the name of Stormatics. But that is not what we're here to talk about. We're here to talk about Postgres performance. Now, what we're going to do as part of this conversation is that we're going to try and understand how Postgres is being adopted across the world, what the difference is between when you start off the development of a new project and when you deploy it in production, and the areas that you can focus on to ensure that your Postgres deployment can actually scale and perform as your application and as your user base scales. And there are 4 areas that we are going to touch on. Query and SQL optimization, performance features, some architectural improvements, and performance tuning. Now, how many over here who have never used Stack Overflow? Yeah, if anybody had raised their hand, I would have called out a liar. So Stack Overflow, what they do is they run an annual survey of their developer community. And in that annual survey, they ask different questions about technologies that developers use. Some of those questions are related to the technologies that developers love, not love, dislike. Actually, they used to use the word hate, but they've removed it, and now it's not loved. Wanted technologies, etc. And what I did was, I picked up the top 5 databases as per DB Engine's ranking, and I looked at their trajectory of popularity based on the Stack Overflow survey over the course of 5 years. And this is the graph that came up. This is the chart that came up. Now, 5 years ago, Postgres was at number 2. And MySQL was actually at number 1. And it had a pretty, if you look at, this is not pointing. This works. Okay, so if you look at the lead over here, MySQL does have a pretty humongous lead. And, well, Oracle has never been that popular. Now remember, we're talking about application developers. That's a Stack Overflow audience. That's a Stack Overflow community. And amongst application developers, Oracle has apparently never been that popular. MySQL has been. And over the course of these 5 years, if you look at all of these trajectories, it's only Postgres that has been consistently growing. And the last survey that was published in 2023 was the first time that Postgres actually overtook all other databases to come out as number 1, the most loved database by application developers. Now, here's another stat that I'd like to share. Now, this is a 2022 report published by Gartner. I don't yet have my hands on the 2023 report, but I don't imagine that it's going to be very different from this one. Gartner says that the database market is at $91 billion, and compared to the previous year in 2022, it grew by 14.4%. That's an $11 billion gain, but the real interesting stat in this slide is right here. 98% of this growth took place in the cloud. 98% in the entire year was in the cloud. And out of that 98%, Amazon, Microsoft, and Google combined own 80% of the market. That is overwhelming. These are overwhelming percentages. And why I point that out? Combine the fact that at this point in time, Postgres is the most popular database amongst application developers, and the database market is growing the most overwhelmingly in the cloud. The question then becomes, what should you do if you want to scale your favorite database on the platform that is the most favored platform? Well, one answer is that you swipe your credit card, throw more hardware at it, and you're done, right? Well, maybe. I'm sorry? Right. And that is what, that is how 80% of the share actually went to the 3 hyperscalers, because scaling by credit card is so easy. But essentially what you're doing is you're delaying the inevitable. If your application is bottlenecking at the database level, chances are that it's not just more hardware that it needs. There are some fundamentals that you need to look at. And those are the fundamentals that we are going to be talking about. Now, as applications are developed, and this is true across the world in any given organization, when applications are developed, there is a lot of testing that takes place, and and as part of that testing, there are different aspects of the applications that are verified to work, and it kind of looks like this racetrack right here. If you develop a race car and you want to test out how powerful the engine is, how fast it goes, how well it corners, you test it out on a track like this and make sure that the car is performing well. But what happens when you push things into production? You encounter something like this. Now, this actually is a picture from my hometown in Islamabad. And believe me, if you're stuck here, it doesn't matter how fast your car is. You're not going anywhere. Right? You're stuck. So the point is, when you do get stuck, the analysis that you need to do is more than just how powerful your car is. Right? There are many, many conditions that need to be met. And when you encounter a traffic jam like that, organizations tend to look for this button, right? Just press a button. There has to be this one setting that will make everything better. There has to be this one tweak that I do, and everything is going to, go well. And that is also why scaling by credit card is so popular. You just swipe the card, and everything is fine, right? But the thing is, I have yet to find this button. I haven't found it. If anybody of you ever finds it, please do let me know, because I'd love to have this. That's what people are looking for. Now, instead of that button, I have 4 broad areas for you today that you should look at. The first one is query and SQL optimization. Second is performance features that Postgres offers. Third is some of the architectural improvements that you can make as part of your production deployment. And the last one is parameter tuning. The first one we're going to tackle is query and SQL optimization. Now, the first advice that I have to share with you is PGStat statement is your friend. Now, what is PGStat statement? It is an extension that is included in the Postgres distribution by default, and it tracks some major statistics about queries that are being executed in the database. It provides a view in Postgres that allows you to understand what queries are taking what kind of resources and what kind of time to execute. There are some stats that are a little difficult to decipher, but I point out 4 over here that are very easy for anybody to look up and understand. The first one is you want to know what are your longest running queries. Right? And the mean exec time will tell you which query is taking the longest to run. And if query is taking too long to run, too long to execute, you want to tune it so that it performs better. The second one is calls, which indicates the number of time a query is called. Now, if a query is being called very frequently, even if it doesn't take too long to execute, the time adds up. And for the most frequently run queries, you want to make sure that your entire stack is absolutely optimized. Standard deviation in execution, which is standard dev exec time. Now, what this tracks is, the simple concept of standard deviation in statistics. And if there is a lot of variation in the execution time of the query, if at one point it is very quick and executes really fast, and at a different point in time it takes longer and executes really slow, then there might be a fundamental issue, an underlying issue that you want to address, because queries typically should take consistent time to execute. And the last one over here are IO-intensive queries. I'm sure that all of you are aware that I/O operations are very expensive operations. The moment you need to go to disk, it takes longer. It is an expensive operation, and you want to minimize trips to the disk. And if a query is, the read time or the write time for a particular query is too big, too long, then it probably needs some optimization. Now, a few things to watch out for when you're working with PGStat statement. It's off by default, so you do need to turn it on. It's highly recommended that for any production deployment, any serious production deployment, PGStat statement is turned on. Now, there is a small overhead. There's a approximately 4% CPU overhead that because PGStat statement does need its own resources to be able to log the statistics that it is logging. But this overhead is well worth the information that you get from the extension. Another thing is, the second point over here, that data is aggregated over time. So you will get statistics from the time that PGStat statement has been turned on, which means that if you tweak something and want to understand what impact it has on the performance of the statistics, you will need to reset PGStat statement. There are some tooling that are available. Cloud providers provide their own tooling, but there are some open source tools available. PGAdmin, PGBadger, and using Prometheus with Grafana are some examples. And then there are some proprietary tooling available as well that you can use if you want to. I've just put in 3 names in here: Datadog, dbeaver, and New Relic, but there are more out there. The second advice in query optimization: explain plan. Now, in order to understand what an explain plan is, let me spend a little bit of time trying to explain what explain is. The way the query planner works in Postgres is that it uses some statistics from the database, and with every query that needs to be executed on the database, it determines different paths that it can take to execute. And then it picks up the shortest path, the most cost-effective path to execute. How it does it? It relies on a few configuration parameters in Postgres config files, and it also leans on some statistics that it gathers for the tables that store the data. And based on what it sees, it calculates the best way to execute a particular query. I'll get into a little bit more detail into what exactly an explain plan looks like in just a minute. But the key areas that you want to watch out for when you open up an explain plan, and when you try and understand how a query is being executed, or how much a step is costing, what are the number of rows that step is fetching, and the width of each row. So these three metrics right here. And the key outputs of an explain plan outline the kind of scan the query planner is going to run, the query executor is going to run, how it's going to join different tables, how it's going to aggregate and group the data that's coming in, and how it's going to sort the data. It gives you all of those details. And you also have the option to run explain analyze. What explain analyze does is that it actually runs the query as well. So when you do an explain and then put the query in front of it, it will give you the explain plan. But if you do an explain analyze, it will actually run the query as well. So if you want to do a delete star from a table, please don't do explain analyze because it will delete all of your data. An example over here, a simple query, well, that is looking up 3 different tables with the intent to figure out what are the top 5 products by sales in the year 2023. The 3 tables are orders, order details, and products. And what it is doing is that it does, the where clause has the dates. It is joining on orders, and it is joining order ID in order details with the order ID in the orders table. And then order details, it is joining the product ID in order details with the product ID in products. And it's grouping by product name, ordering by total sales descending, and limit 5, which will give you the top 5 sales in the year 2023. Now, if you run explain on this query, this is the output that you get. Now, to somebody who's looking at an explain plan for the very first time, this is a lot of gibberish, right? It's like, what is going on over here? But a few key things. Again, the idea is that for anybody who's not a Postgres expert, you should be able to do something as simple as this. Assuming that we're talking to application developers and architects, etc., this is something that developers are able to handle. Now, one of the first things that you'll notice in this output is that it's nested. So you will see indentation. And much like any software program, the most indented line is the one that is executed the first. So that's where you start. You start by this filter, which is ordering, which is the where clause. And what you see over here is that it's going to run a sequential scan, and the startup cost is 0, and the ending approximate cost is 225. It's going to fetch 2,000 rows, and each row is going to be 8 bytes wide. Okay? So that's the information that you're looking for. So you want to make sure that at any stage, if you are expecting an index scan, you're not getting a sequential scan. Or if you're expecting a sequential scan, you're not getting an index scan. And the cost looks reasonable, and the number of rows that it's fetching, it's something that you expect. And as long as you're looking at these 3 items, you should be fine. So at each stage, just understand what the startup cost is. Over here is 250, which is the hash join, and the join condition is product ID in the products table with the product ID in the order detail table. The startup cost is 250, the ending cost is 600, and if you expect this to be lower, then you need to look at this part of the query and then optimize it. Again, just going back to this slide for a little bit over here, the 3 metrics that you need to understand are cost, the number of rows, and the width of each row. In order to help the query planner do its job, run analyze command periodically, because what analyze does is that it updates the statistics of the tables in the database, and it helps the query planner plan accordingly. And also, You can tweak the database parameters in the configuration files a little bit in order to make sure that the query planner is using the right numbers to calculate the correct path. More on this a little later. And lastly, in query optimization, watch out for locks. Now, what locks do, let's say you have one session that is going to update a particular row in a table. Over here, it is updating foo and is setting something where ID is 1. And the moment you execute this command, this session gets an exclusive lock to this row where ID is 1. When you execute the next command, it gets an exclusive lock where ID is 2, and so forth. And it retains this lock till the whole transaction is committed. Now, from this point till this point right here, where this is committed, ID 1 is going to be locked. Now, if there is another session that is trying to update the same row, it could be a different column that it's updating, but if it's trying to update the same row where ID is 1, this will just end up waiting. It will wait till the commit is executed and the lock is released. Now, if you have long-running transactions that are requiring exclusive locks, understand that other sessions are going to end up waiting, and that is going to slow down the overall performance of your database. It's very important that if you acquire an exclusive lock, you release it as quickly as you can. That's the third tip in query optimization. Key takeaways from here: make sure that you're monitoring your queries so that you understand what's going on. You analyze the execution, so you also understand that they're being executed the way you expect them to execute. And you write your code such that it avoids locks to the extent possible. Moving on to the next section, which is performance features that are available in the database. By the way, is somebody keeping time? I don't think I am, but please, keep me honest on time. So, with performance features that Postgres offers, the most obvious one of them is indexes. Now, what indexes do is that they help look up data faster. Think of it as a table of contents in a book that you're reading. If you want to navigate to a certain section of the book, you can look up the page number of that section and immediately go to the page number rather than scanning the whole book and then trying to understand where that chapter, where that section is. Similarly, indexes are like a lookup table for understanding where to get the data from. The default index is the B tree index, which is a balanced tree. That's the default index that Postgres is going to implement if you if you want to index a column. There are different types of B tree indexes that you can implement. One of them is composite. If you have multiple columns that you are looking up, you can write a composite index that includes all of those columns. You can have a conditional clause that will only implement a partial index. And the benefit a partial index gives is that it takes up less space. It doesn't index the entire table, it will only index partial, and it will take up less space. And then there's a covering index. Now, this is a little confusing because it's hard to understand how that is different from a partial or from a multi-column index. But what covering does is that it uses the keyword include in the clause when you implement that index. And if you usually fetch data in a way that there are multiple columns that are being fetched and only one of them is indexed, then if you include the other columns in the index command, it will sort the database will sort the data in a way that the other columns are also fetchable quickly along with the indexed column. So if you don't use include, what will happen is that the indexed column is going to come up very quickly, but the rest of the data might take longer. With the covering index, you can avoid doing that. A hash index not the default. You have to specify a hash index, and what it does is that it does an equality check, which means that if you are looking for, if your where clause is for being equal to a certain value, you can look it up very, very quickly. That's how hash index is implemented, and the complexity is order of 1, which means that no matter how big your table is, the execution time is always going to be constant, consistent. Brin indexes are another very specialized type of index, and what a Brin index does is, instead of storing the entire data, if the data is spanning over multiple blocks of storage, what it does is it, for a particular block, it stores only the starting and the ending value. And if you look up that particular index, it will know which block of data to go to and retrieve that data very quickly. So it saves a lot of space. Instead of storing the entire index in the entire column or the entire table, it will only store the smallest and the largest values in a particular block, and then take it from there. Now, indexes are not a one-size-fits-all, so be careful while using them as well. And these are some of the conditions where there's a recommendation against using indexes. If you need the entire data of the table anyways, the index is just taking up space. It's not doing anything. The query planner will also run a sequential scan. It will not do an index scan, and you're just wasting space. If your workload is heavy on writes and updates, understand what data is sorted already. So when you ask for a sorted result, it will incrementally sort data as it joins it, as it combines it and groups it, rather than doing it all from scratch. Sorry. And then auto vacuum. Now, this is the roots of auto vacuum, and the need for auto vacuum are in MVCC, which is multi-version concurrency control. That's how concurrency is implemented or facilitated in Postgres. That's a topic of a different conversation. I won't go in there. But one of the things that MVCC implies is that there are dead tuples in the table, and it can cause bloat in the table as time progresses and as data is updated. And periodically, you want to remove that bloat, you want to remove those dead tuples, and that's what auto vacuum does. There are a few tuning parameters that you can fine-tune for execution of both the auto vacuum and parallel queries based on your own hardware availability and your use case. But overall, these features will just work in Postgres. Key takeaways from this section, the performance features. Indexes are a powerful ally, but don't overuse them. And pretty much let Postgres do its job. It's pretty intelligent in doing that. The third section is about architectural improvement that you can make in your Postgres deployment. And the first topic that we're going to tackle over here is load balancing. Now, what load balancing does is it distributes the load of your database queries and execution across different nodes so that one node doesn't become the bottleneck. That's the whole concept about it. And the benefit that you get is that a single node doesn't become the bottleneck. That's not where you're constrained. It facilitates the concept of horizontal scaling, and it also increases the resilience of the system in case of a failure of one of the nodes. Try to implement a visual example. The left diagram over here is without load balancing, and you see a Postgres database that is talking to the application. So both write and read operations are taking place from this particular node, and any analytics that are being run on that data, any reporting that is being run, is also done on the same database. Now you do see that there are a whole lot of arrows coming in and going out of this same database, and this little guy over here is trying to facilitate a lot of operations. Now, in such a scenario, what happens is that if this load increases, this thing slows down. And if this increases, the application slows down. And that's a very common scenario that we come across as we work with databases in production. And the easiest way to get around this problem is to split up the load, balance it across different servers. And this is an example of how it's done. Now over here, you've got a primary database that the application is writing to, and it replicates data to 2 standbys. And one of these standbys is being used for read operations to the application, and the other standby is being used for reporting analytics. Now, each node now only has one thing to take care of. This node is taking care of writing and just ensuring that it's available for replication. This node right here is available for read requests that come in from the application, and this node right here is available for the read requests that come in for analytics. And if any of these loads increase, the other part of the operation are not going to get impacted. So that's the benefit of load balancing. Now, what I did was I ran a very simple PG bench run. That's the most favored benchmark in the Postgres community. And I did a single node. I did single node selects and 3 node selects in that PG bench run. And this was on my own laptop, so it's not a distributed system in any way. Just on a single machine, 3 nodes up and running, and comparing the performance. And even when sharing hardware, I saw that the TPS went from about 372 to about 486. That's a 30% increase in performance. Sharing the same hardware, sharing the same resources, just making sure that there are 3 separate servers that the application is reading from. Now, imagine how much of a performance boost you can get when you actually split hardware and add, spin up these nodes on different servers. The second area that you can look at is partitioning. Now, what partitioning does is when a particular table grows very large, you can partition it by a certain criteria into smaller segments so that when you have queries running, either reading or writing, it's a smaller segment that they target rather than the larger table. Any table that grows too large is going to become difficult to manage, and the performance is going to deteriorate. And if you split it up into different partitions, you will get a boost in that performance. And those are some of the benefits that you can get. You'll get a performance boost. Maintenance is going to become easier, and the indexes are also going to be smaller for the smaller chunks. Visually speaking, let's say you have a case where you are storing data by date, and you've got 12 months in a year. And one way to do it is you have a single table that has all 12 months of the year, and that contains all of the data. Or you could partition by quarter. So January, February, and March are in Q1. April, May, and June are in Q2, and so on and so forth. So you've got 3 months each in these partitions. Now, visually, what happens when you run a query? Now, when you try and look up something where the month is August, in this particular case, Postgres is going to run a scan on this entire table to try and figure out where August is, and then retrieve data that is related to August. Now, this is a 12-month table, which can potentially be very large, and this operation can potentially be expensive. Now, if you partition it by quarter, Postgres will know that it can ignore Q1, Q2, and Q4. So 3 segments are completely ignored. And it zeroes in on Q3, and that is where it gets its data from, allowing for significantly faster data retrieval and much better performance. Key takeaway from architectural improvements is, well, just one. Just don't overload a single node. If you feel that a single node is being overloaded, split up the load, scale it horizontally, and you will get better results. The last section of this presentation is on parameter tuning. Now, there are 2 broad categories of parameters in Postgres. Allocation parameters, where you allocate certain resources to the database. And the second is cost definitions, where you help the query planner understand what the cost is for executing a certain operation. These are 2 types of parameters that are available. This slide gives you examples of parameters that are allocation related and that can be very easily tuned by anybody who has some basic knowledge. Shared buffers, wall buffers, and work mem. Now what shared buffers does is it allocates the cache for frequently accessed data. Now, I'm sure all of us are aware that accessing data from disk is significantly more expensive than accessing data from memory or from cache. And what shared buffers does is that it allocates a part of the system memory to cache, which makes frequently accessed data, more easily accessible and faster. The recommended value of the default is 128 megs, but the recommended value is between 25 to 40% of the available system memory, and you can tune it according to your own requirements. Wall buffers. Wall stands for write-ahead logs, and the way Postgres works is that for any data that is being processed or it's written, it first writes it to write-ahead log, which is stored in the wall buffers, and then it is flushed to disk and actually written to disk. And if you increase the size of these wall buffers, the frequency of actually flushing to disk decreases, and that helps you with more efficient operations. Of course, you need to kind of balance out the fact that anything that is in buffer is not yet written to disk, and in case the database crashes at that point in time, that data is going to get lost. So you need to balance the availability of the data or the requirement of the availability of data with the need to speed up the operations. Typically, the default of wall buffers is 3% of shared buffers, and for very highly concurrent workloads, a value of 16 megabytes can help with faster performance. Work mem is the memory that is available for a single thread of operation in any query. Now, if there are multiple paths that a query is taking and multiple operations that a query is doing, each one of those paths or each one of those threads is going to be allocated this amount of memory. The default is 4 megabytes. And if you have a very high I/O activity, if your query and your workloads are I/O bound, disk bound, then a higher work mem can help you speed things up. Now we can talk about cost parameters. Now, remember in one of the previous slides, we said let the query planner do its job, or help the query planner do its job. And there were two things that we talked about. One was database parameters, tuning parameters, which was discussed in the previous slide, and the other was cost, allocation of costs. Now, this is not allocation. This is just to give the query planner an idea of how expensive or inexpensive a certain operation can be. CPU tuple cost indicates the cost of processing a single row of data, and a higher cost, what it encourages the query planner to do is process less rows at a time, and for any operations that are bound by CPU, a lower value is going to help. If your operations are bound by I/O, then a lower value, sorry, the previous one was a higher value, then a lower value is going to help if your operations are bound by I/O, because that will encourage the query planner to do more CPU-oriented stuff. Random page cost talks about how expensive it is to access a non-sequential bit of data on your disk. Now, for SSDs, which are very common nowadays, a smaller value means that you can very quickly access random data on the SSD. For magnetic disks, spinning disks, a higher value is more desirable because accessing sequential data is cheaper, random data is more expensive. Effective cache size is the expected size that a query planner should have access to in terms of cache, and it includes both the database cache and the operating system cache, so it combines the two together. The default is 4 gigabytes. This is not an allocation, this is an idea to give to the query planner. Higher values imply that more data is available in cache, and it encourages index scans, which is random scans, random access of data. And lower value of effective cache size, what it does is it encourages sequential scans because it implies that data in cache is less and you will need to access data from the disk. Takeaways from parameter tuning: tweak the configuration based on what your hardware looks like, what resources are available, and what your workload looks like. This will require some experimentation. There's no magic formula that you can use to implement. These are just best practices. So it will involve a little bit of hit and trial before you get it absolutely right, which also makes it a very ideal candidate for artificial intelligence-based tuning. And there are tools available for that. And lastly, in conclusion, again, going back to the slide that we had on scaling by credit card, that should be the last resort, spending more money on hardware. There are lots of things that you can do, even without being Postgres experts, to make your database perform better. And try out those things first, all of the things that we've discussed in this presentation, before you spend more money on hardware. Brings me to the end of my presentation. That's the QR code for my LinkedIn. I'm happy to connect with people and answer any questions that you might have. And I'll take questions related to this particular presentation, if any.